Hello, my name is Roy Simpson, and I'm a professor of mathematics at Cosumnes River College in Sacramento, California. This video, we're going to talk about computing work. So this is for a Calculus 2 or an integral calculus course. And we're going to hold ourselves to some prerequisites here. The prerequisites that you're going to need specifically for this problem will be trigonometry. You have to know your trig, and you'll also have to remember parametric equations. Of course, I'm actually going to help you out here by talking about parametric equations a little bit, but it is important that in a course like integral calculus that you do review parametrics, because at some point, especially I think about halfway through, you're going to end up running into them on a pretty consistent basis. So let's go ahead and read this problem. A particle is moving along a path defined by the parametric equations x, which is defined to be some constant r cosine of t, and y of t, which is a constant r times the sine of t. And we're going to start this movement at time 0. And the tangential force, the force that is being exerted on the particle at any given time t is equal to the absolute value of the x coordinate. Okay, and our goal is to find the total work done on the particle. Now, a few things that we're going to remind ourselves of. First, since we're finding the total work done, let's just write down the general formula for work again. So that first concept is that work must be the product of force that's acting on an object or a particle through the distance that particle is moving. And in this case, we know that the force is going to be equal to the absolute value of the x-coordinate at any given moment, and the x-coordinate is defined as a function of time, so the force is going to be a variable force. The second piece of required knowledge that we are going to have to use here is the idea of a parametric equation. And really the idea of a parametric equation is that you're given the coordinate for the x value in terms of some function. So x is some function of time, and the coordinate for the y value is given as another function, possibly the same function, but generally not. So y is some other function of time. And then as time moves forward, it's like an Etch-a-Sketch. If you remember an Etch-a-Sketch, you had two dials. One dial controls the horizontal sketching, and the other dial, the rightmost dial, controls the vertical sketching. And so you can think of it this way, that f of t controls the horizontal sketch, and y of t, or g of t, sorry, controls the vertical sketching. And so these two things operate independently. The nice thing about a parametric equation, or parametric equations, if you want to say it that way, is that you can get very complex looking graphs from a set of parametric equations. So that's what we can get off this. Although this will not be terribly complex, we're going to go ahead and showcase how to relate these two together. In fact, part of that knowledge base of parametric equations is knowing how to relate the variables together. And this is called eliminating the parameters. So let me write that down. And this is a topic that you should have learned possibly back in your pre-calculus course, but it's probably been a couple semesters, a year or something like that since you've really dealt with this. So when we eliminate a parameter for a given parametric equation like this, x equals r cos of t and y equals r sine of t, generally speaking, if it's a simple parametric equation, something like, for an example in a different color, if you had something like x of t is equal to t plus 3 and y of t is equal to, let's just say, t squared, then you can eliminate the parameter here by solving the first equation for t. So you could say that x minus 3 must equal to t, and then plug that into the second equation to create a relationship. Since t is equal to x minus 3, t squared must be x minus 3 quantity squared, and then you have a nice look to your, or a relationship between your x and y. This will look sort of like a parabola. However, you should note that the domain and range of your parametric equations will determine what the true look of your your graph is going to be, because sometimes you get weird situations, actually fairly common, in fact, that with parametric equations, your x values may be magically limited to be positive, and so that really kind of fixes what the graph is going to look like. That's something that you can review in your old pre-calculus book, or as you move forward in this course, because you're going to be running into it again. But in this case, with these functions, let's see how we can relate x and y together. And think about this. Is there a way to relate cosines and sines together in a single equation? And I hope that you remember this from your trigonometry. So this is where I say you need the trig prereq. You should recall that the cosine squared plus the sine squared, let me write this down, cosine squared of an angle plus sine squared of an angle should be 1. Therefore, if you multiplied, well, maybe I won't multiply. Maybe I'll say, therefore, if I took this x squared and this y and squared it, I would get r squared cosine squared plus r squared sine squared. And if you imagine being able to factor out the r squared, that's just r squared times 1, or in other words, r squared. So now that we know that r times cosine quantity squared plus r times sine quantity squared is equal to capital R squared, well, we know therefore that x squared plus y squared is equal to r squared, which means from our algebra prereq that we have a circle of radius capital R centered at 0, 0. So, okay, so that's what these parametric equations are going to look like. It's a circle of radius capital R centered at 0, 0. So I'm going to draw that really quickly here. And now the next thing we need to do, again, just to recall with parametric equations, is to note that we're allowing this set of parametric equations to run from time equals 0 to whenever we get to a negative r comma 0, the point negative r comma 0. And I purposefully mixed these two ideas. So it's starting at time 0 and ending at negative r comma 0. So at time 0, let me go ahead and write this out. At time 0, I'm just going to create a time versus x versus y. Well, if you consider that x is the cosine, r times the cosine, then at time 0, the cosine of 0 is 1. So this is 1 times capital R. And y is r sine of t, and at time 0, sine is going to be 0. So there we go. At time 0, we start at r comma 0. Now, just to fast forward a little bit, you don't have to go crazy here. Just fast forward a little bit. Time pi over 2, because we're dealing with trig functions. It'd be easier to work with radians here. So at time pi over 2, let's see, x is again, capital R times the cosine of time. So the cosine of pi over 2 is 0. And y is equal to r sine of time, and sine of pi over 2 is 1. So r times 1 is r. So at time pi over 2, we're up here. So here's the path, the directed path of travel for this particle, and I'm going to just go ahead and say that it continues until we get to here. This question's sort of flawed, because I should say in my language for the question that a particle is moving along this path starting at time equals 0. Find the work done on the particle by the time it reaches negative r comma 0 for the first time, because it will actually continually circle around or go around that circle. But in reality, we just want to know how long, or we want to know when it gets there the first time. Now here comes a pretty challenging piece here, because we need to now kind of translate all this into a work problem. So let me scroll down here and say, okay, well, we recall that the work moving in the ith piece, let's just say, is the force to move us along in the ith slice times the distance that we're moving in the ith slice. So let me just showcase an ith slice. Now, this is where you're really going to have to think, because a little slice here, it happens along the circumference, right? Our steps, our baby steps here are happening along the circumference of this circle. Now I'm going to overly exaggerate this. I'm going to make this ridiculously exaggerated. So let me capture this picture and then zoom in. All right, there's our zoomed in piece. And I'm going to, again, this is going to be super overly exaggerated, but I just want to really convince you of what I'm doing here. So let's just say our steps, and remember, we're supposed to integrate in the long run. So we want to take infinitesimally thin steps in the long run. But for now, let's suppose that we have a step size that starts here and goes to here. So this piece is the ith step. Let's just pretend that's the ith step. So what is the work done pushing the particle along that ith step? Let me scroll over to the left here where I was doing all my work before. Well, we had said that the work was going to be the absolute value of the x coordinate. So that's going to be the absolute value of the x coordinate at that time. And in fact, maybe I should say x at, well, I'll just say x sub I. Technically speaking, I should say x at time sub I, but whatever. And I'm really butchering my notation. And times the distance or the wiggle of our movement, that little step. So I'm going to go ahead and go over here and say, well, that's some change in distance. It's not a delta x, actually, and it's not a delta y, because it's not in a horizontal direction. It's not in a vertical direction. It's along an arc, and that's going to be a critically important statement in a moment. So I'm going to, for now, call that a change in distance. So if you take a look at this, again, we were told at the beginning of the problem that the tangential force, that means the force that's happening at time t, is equal to the absolute value of the x coordinate. Okay. Well, let's go ahead and replace that absolute value of x sub I with this guy right here, with r cosine of t. Might as well. That's a freebie. That's something that we're told, so we can go ahead and take advantage of that. So I'll scroll down here, and I'll replace this absolute value of x sub I with an absolute value of r times the cosine of t sub I, where t is just, we don't know what time it is, but it's some random time in that step period. So t sub I is some clocked time value that occurs within this arced range, okay? So it might be time equals pi over 6, it might be time equals pi over 3 or something like that, or it could be pi over 7 or something like that. We just don't know, okay? And then finally times a wiggle along the arc. Now, to be very fair, you should recall from your trig course an arc length formula. And to showcase that arc length formula, to remind you, I'm going to go back over to this big curve, and I'm going to just showcase this sector here. And we knew from trigonometry that the length, the arc length, is equal to the radius of the circle times the angle that you're cutting out. So this angle right there, that's what that arc length is supposed to be. Specifically, in our case, we're calling that delta D for some reason. So that wiggle in arc length is supposed to be R times the angle. Now this is, okay, we're almost ready to use this relationship. However, if I say that delta D is R times theta, I have no idea what theta is. So that's a problem. If I scroll back here to my equation, that work is force times distance, and we were told the force is r cosine of, the absolute value of r cosine of t. And if we were to place that delta D, in fact, I will for the moment, if I were to replace that delta D with, let me go ahead and do this, and r theta. Now look at all the variables I have there. It looks like I have a lot, but actually I have two right there. I have those capital R's, but they're not variable. Those are constants. And I have a time variable, and then I have a theta variable. Let me go ahead and just show that in here. I have a time variable right here and a theta variable right there. That's not going to do. You can't integrate anything like that. But luckily, if you think about what the angles are, and if I go back here to showcase this, notice that at angle 0, it was time 0, just happened to work out that way actually. At angle pi over 2 here, it ended up working out that that was actually time pi over 2. And finally, at angle pi, which gave us this relationship, and let me go ahead and highlight where that angle lands. At time pi, we were actually at angle pi. So it turns out these times are actually equivalent to the angle that we're facing. So we can kind of consider, not just kind of, we can actually consider that this little sliver of theta is just a wiggle in time, because the angle theta, this total angle right here, if I called that total angle theta, well then theta is equal to time, right? Because if you open to a pi over 2 radial angle, you're going to land at this point at time pi over 2. It just happens to be in this problem that it works that way. So if I want to make it more interesting, I want to talk about this sliver, I could say, well, this sliver is just a wiggle in time. In other words, theta, our theta that we see in that sliver, is just a wiggle in time. Since theta is the same thing as the time, that little theta right there, which is technically a wiggle in theta, is a wiggle in time. And so now I can go say, all right, well, the delta d, the change in distance, is r times change in time. And that is the key here, right? So I can go back over here and I can say, great. This tells me that I have the absolute value of r cosine of time times r times the change in time. And now we know we can integrate from time 0 to time pi, because that's when we would get to the point negative r comma 0. Another thing I should mention here before I begin is I didn't actually say it in the problem, but I should have told you that r is greater than 0. R is not negative, r is greater than 0. And so that way I can then make the assumption, or not the assumption, I can make the mathematical move to move this value of r right here outside of the absolute value. And so we end up having the following. The work for the ith step is going to be capital R squared times the absolute value of the cosine of the time step times the wiggle in time. Now I'm ready to compute the work done on this particle. This also, by the way, this problem requires you to remember how to integrate an absolute value. This is kind of a tough problem. This is not a problem that I would expect most students the first time they've dealt with a work problem to be able to do. That's why I'm doing it in a lecture video, right? So, okay, the total work done is going to be, we're going to integrate this work formula here. So capital R squared times the absolute value of cosine of t dt. And we're going to do that from time 0 to time pi. Now, let's think about the cosine curve. Again, another recall from our work in the past in trigonometry. The cosine curve looks like this guy right here. I chicken scratched it out, but that's good enough. And you could see that the cosine curve goes from being positive to being negative at time pi over 2. So I need, remember, the absolute value takes negatives and makes them positive. So I'm going to have to take the opposite of my function cosine of t once I reach the time pi over 2. So I'm going to break this integral into two pieces. The piece from time 0 to time pi over 2, well, cosine is already positive from time 0 to time pi over 2. It's already above the x-axis, so there's no need to have absolute values. However, from time pi over 2 to time pi, we have a problem, right? The cosine from time pi over 2 to time pi is negative. And if I want to rip off these absolute values, let me highlight them. If I want to rip off these absolute value signs, well, I have to force the cosine to be positive. Right now, between time pi over 2 and time pi, it's negative. So to force it to be positive, I need the opposite of the cosine. I need the opposite of the cosine. If I do that, now the opposite of the cosine on that interval will actually be positive. Now I can do some mathematics. Factor out the r squared. Change the pen size. I'm using a small ink here. We're going from 0 to pi over 2 of the cosine dt minus, because I'm factoring the negative out, r squared integral from pi over 2 to pi of the cosine of t dt. The antiderivative of the cosine is the sine in both of those cases. So this is going to be r squared times the sine of t from 0 to pi over 2 minus r squared times, again, the sine of t, this time from pi over 2 to pi. And let's go ahead and compute. Sine of pi over 2 is 1 minus the sine of 0 is 0. Minus r squared. The sine of pi is 0 minus the sine of pi over 2 is 1. That's going to be r squared minus a negative r squared, or in other words, 2r squared. That is the work done in moving the particle from position r comma 0, let's get right here, all the way along the curve to negative r comma 0. And again, this is a very tough problem, one that would be very challenging, a good project level problem, but other than that, it would be terribly challenging if it were given on an exam, for example. That'd be terribly challenging. But it showcases something you're going to see very shortly in this class, which is, what if I want to calculate a wiggle, but the wiggle is not in x and it's not in y, but instead along some type of arc? Well, I happen to know that along an arc, I can find the distance. The distance is s equals r theta. We used it over here, right? So I can use that formula to help me figure out the wiggle and distance. Not all of them will be like this, but we'll have a general formula in the long run.